The following proposition is an extension of the Bolzano-Weierstrass theorem. Now, in the Bolzano-Weierstrass theorem, we assumed that the sequence n was bounded, and then we said that it has a convergent subsequence. Now we do not assume that the sequence is bounded. We just assume that n is any sequence. Then we claim that it has convergent subsequence in the generalized sense. So we've actually defined previously that convergence in the generalized sense means that the sequence limit exists, which means that the sequence either converges to a finite real number, or it converges to positive infinity or to negative infinity, but the situation where the limit exists is better when the limit does not exist, because when the limit does not exist is equivalent to the sequence having could have lots of partial limits, and it could oscillate between them. Basically, it's not informative at all. Whereas if we know that the sequence converges to infinity or tends to infinity, right? We previously said that it diverges to infinity, but nevertheless we know that the sequence is unbounded above, and we can find within the sequence values that are arbitrarily large. So let's start by proving this proposition. So it's quite straightforward. So suppose that the sequence is bounded first, then we immediately apply the Bolzano-Weierstrass theorem, and then we say, okay, if n is bounded, right, then it has a convergent subsequence, and Bolzano-Weierstrass theorem comes to the rescue in this case. Now, what happens if the sequence is unbounded above? Then we will show that it has a subsequence that would converge to infinity or diverge to infinity, whatever. So if we have sequence n that is unbounded above, then this means that no number is a bound above for the entire sequence, meaning that for every number, say for 1, we can find an index such that an element of the sequence with this index will be larger than 1. And similarly, we can do it with any number, right? So now we're going to make the inductive step. Basically, we're going to construct a subsequence of a n, which is going to converge to infinity. So the inductive step is to assume that we have already defined or found a chain of indices, n1 up to nk, that are increasing, right? This is a condition for it to be a subsequence, such that for every one of those indexes, for every m in 1 to k in this set, a with the index nm would be greater than m. And basically, we need to show that we can continue this construction one more step, and that would conclude the inductive construction. So again, applying the same argument, since n is not bounded above, there are actually infinitely many indices n, such that an is greater than k plus 1. And why is that? Because if there were only finitely many elements of the sequence an that are greater than k plus 1, right, then we could just arrange all those, consider them as a set, all the indices, all the finitely many that are greater than k plus 1, and then every finite set would have a maximal element, right? And so the sequence, the part of the sequence, the first part would be bounded by m, and the second part of the sequence could be bounded by k plus 1, right? And then we would conclude that the sequence is bounded. Therefore, we cannot have the case that we have only finitely many elements of the sequence that are larger than k plus 1, or any number, right, in case of an unbounded sequence. Okay, I hope it was clear enough. We've invoked similar arguments previously in the course, right? So now we can find any such index, since there are infinitely many of them. We can take any index out of the infinitely many and call it nk plus 1 on the condition that it would be larger than nk. And since there are infinitely many such indices, then we can guarantee that we can choose an index that will be greater than nk, right? And then nk plus 1 was chosen in a way that a with the index nk plus 1 will be greater than k plus 1. And therefore, we have extended this collection of indices n1 up to nk plus 1 such that for every m in this set, we have that a with the index nm is greater than m. And now what we need to do is just to observe this subsequence. We've actually constructed a subsequence of an k, and this is a subsequence of an, and for every k we have this property by construction that a and k is greater than k, and now we're going to invoke the limit arithmetic theorem to infer that this sequence has to converge to infinity, right? Basically the sequence can be as big as we please, provided that we go far enough, which means that the limit is infinite, right? So, but this implies that the limit converges to infinity because by the generalized limit arithmetic theorem, because the limit of since a and k is greater than the sequence that converges to infinity, then it has to converge to infinity. And now, if we were to look at the sequence an, which is not bounded from below, so to save the effort, actually it's very similar, but a nice trick would be to consider the sequence minus an. And then minus an, if an is not bounded from below, then minus an is not bounded from above, right? And then we can find a subsequence of minus an that would converge to infinity, which means that an, by the generalized limit arithmetic theorem, has to converge to negative infinity, right? So basically, we have it here. So using the previous step, we can choose the subsequence such that limit of minus a and k would be infinite. And therefore, by the limit arithmetic theorem, which is the generalized version that we proved previously, it would infer that a and k converges to negative infinity. Great. So let's proceed. Okay, and so we continue this theorem in the same spirit. So let an be a sequence that is monotone increasing or decreasing and unbounded above and correspondingly unbounded from below. Then such sequence converges to either plus or minus infinity. So basically we're stating two propositions in one here, which is the extension of the monotone convergence theorem. So previously we said that if we have a monotone sequence which is bounded, then it has to converge. And it was tightly related to the concept of the axiom of completeness, but it was quite natural that a sequence that is monotonically increasing and yet bounded above has to converge to the finite limit. And we actually showed that the supremum is the limit of the sequence, the lowest upper bound. But we assume the sequence is bounded. Now, when the sequence is non-bounded above and is monotone, it basically has to converge to infinity. And if it's not bounded from below and monotonically decreasing, it has to converge to minus infinity. So to prove it, we'll invoke a very similar construction to the one that we've seen in the previous step, right? So if the sequence a and m is unbounded above and monotone, it means that for every positive m that we take, m is not a bound above for the sequence, right? And if it's not a bound above for the sequence, it means that there exists some index such that an element of the sequence with this index is going to be greater than m. This is exactly stating that the positive number m is not a bound above for the sequence, any positive m, right? Because for any positive m, it's not an upper bound for the sequence. That means that there is an element of the sequence which is greater than this m. And for such m, we can find an index n that might depend on m, at least one, such that a with this index would be greater than m. Actually, we can always find infinitely many such indices if the sequence is unbounded above, right? Okay, but this is not enough. We actually need to use the condition that a is monotone in order to prove that it diverges to infinity, right? Because being unbounded above does not guarantee convergence to infinity, because it can oscillate, for example, between positive and negative infinity, right? So now we need to use the condition of monotoneness. So since n is monotone, this means that for every n that is greater than this index that we found, the element an would be greater or equal to A and M, right? Because if N is greater than an M, and the sequence is monotone, this means that the element of the sequence with the bigger index is going to be bigger. This is the monotonicity condition. And A and M, as we know, is greater than M. And basically what we've proved now is we've proved that AN converges to infinity according to definition. Why? Because note that we have demonstrated that for every positive number M, we can find an index n of M such that for every n that is greater than n of M, AN would be greater than M. And if you recall, this is exactly the definition of convergence to infinity. And the case with negative infinity and when the sequence is bounded below can be done similarly, or we can use or invoke the same trick by observing the minus of the sequence, right? So if the sequence AN is monotone and unbounded from below, then we can consider the sequence minus AN, and this sequence would be monotone and unbounded above, right? So it's monotone and unbounded above, then it has to converge to infinity, which means that the original sequence has to converge to negative infinity. Okay, that was a bit technical, but hopefully clear enough. Not conceptually hard. Okay, and now we need to talk about partial limits. So basically, we have a sequence AN, and the number L is a partial limit if and only if for every epsilon neighborhood of L contains infinitely elements of the sequence. Basically, this is a restatement in terms of, so to say, topology or open sets, because in this course we're bringing ideas from topology and metric spaces just to give the flavor of it. So let us recall that a partial limit of the sequence is a real number such that the sequence has a subsequence that converges to this real number, right? But then here's an equivalent definition or formulation or condition for a real number to be a partial limit of the sequence, right? So one would say one way to say that L is a partial limit of the sequence, the original definition, if there is a subsequence of the sequence that converges to L, right? Where we're saying that this is equivalent to saying that every epsilon neighborhood, basically every open interval around L, would have to contain infinitely many elements of the sequence AN. Okay, so let's proceed with the proof. So suppose that L is a partial limit of the sequence. This means that by the definition, there is a subsequence that converges to L, right? So we can observe this subsequence. So let A and K be such a subsequence that converges to L, right? And then we would actually apply the definition of the limit for this subsequence. Okay, so since this subsequence converges to L, then by definition, this means that for every epsilon, we can find a natural number n of epsilon, such that for every k that is greater than n of epsilon, the distance between this element of the subsequence and the limit is smaller than epsilon. Now, if we unfold this absolute value inequality here, what we obtain is that this inequality is equivalent to that, or this is equivalent that A and K, yeah, if we just add L and to all the sides, this means that A and K is between L plus epsilon or L, and at the same time is greater than L minus epsilon, which means that A and K belongs to this open interval around L, right? And this holds for every K that is greater than n of epsilon, which means that there are infinitely many elements in this open interval around L. And this holds for every positive epsilon, which means that every epsilon neighborhood of L contains infinitely many elements of the sequence, or you could argue that every open interval or every open set containing L would have to contain such a symmetric interval for some epsilon, and therefore every open set containing L would have to contain infinitely many elements of the sequence, right? Okay. So basically what we have shown, to summarize, that for every positive epsilon, there exists a natural number n of epsilon, such that for every k that is greater than n of epsilon, and k is in this interval, which is equivalent to saying that every epsilon neighborhood of L contains infinitely many elements of the sequence AN. So basically, I'm just gonna say something that, to give you some flavor of generalization. Don't worry if it's not clear at this stage, but just to give you some flavor how we can generalize the notion of a partial limit to a metric space, basically saying that every open ball around the partial limit, or around this element L of the space, would have to contain infinitely many elements of the sequence. Then this L is a partial limit of a sequence in a metric space. But even when you don't have a metric and you only have the notion of open intervals, which is basically the notion of topology or a topological space. Now, don't worry if this is a bit unfamiliar. I'm just giving the flavor of what's to come in the future. So whenever we have a notion of open sets defined, that's the most general context is a topological space, then we can define the notion of a partial limit of a sequence. If we have a sequence in a topological space, then we can say that the sequence, that an element of the space is a partial limit of the sequence if every open set around L would contain infinitely many elements of the sequence. Okay. So, and conversely, now we are going to prove the converse of the statement. Suppose that every epsilon neighborhood of L contains infinitely many elements of the sequence AN. Basically, we now need to use this to construct a subsequence of AN that would converge to L. Okay, and basically the idea is that we'll take shrinking intervals, which are open around L, and we will choose an element of the sequence in each such interval, because each such interval contains infinitely many elements. So let's see how it's done. So we're going to construct a subsequence of AN that is going to converge to L. Okay, so this is a standard trick. So consider this open interval or neighborhood of L. Then by our assumption, it contains infinitely many elements of the sequence. So we can find an index, natural number n1, such that a(n1), a with this index, would be in this interval. Well, because this interval contains infinitely many elements of the sequence, so we may as well choose 1. Okay, and similarly, now we're going to make the inductive step or assumption. Suppose that we have already defined k indices that are increasing, such that for every k, a and k is in this interval. Okay, and we need to show that we can extend this sequence to one more step. This would be the inductive proof or inductive constructions. Okay, and now we look at this open interval. So since this neighborhood, remember this is 1 over k plus 1 is positive, so that's a neighborhood of the limit L. So by assumption, this open interval around L contains infinitely many elements of the sequence. Then we can find an index nk plus 1 that is going to be greater than nk. Why? Because we have here infinitely many elements. And so we can choose one with index that is greater than nk. This is the assumption that we have infinitely many elements in this neighborhood, such that a nk plus 1 is going to be in this interval. And basically, now we have completed the construction of the subsequence of AN. So we have constructed the sequence A and K. Basically, in each such interval, we choose one of the elements, because each such interval contains infinitely many of them. And by construction, each such element of the subsequence has to satisfy this condition. And now we can apply the sandwich theorem to conclude that A and K has to converge to L. All right. So using the sandwich theorem, this implies that A and K converges to L because this sequence converges to L, this one converges to L, and by the sandwich theorem, A and K has to converge to L as well. Okay, and that completes the proof.